In section 11.5, we are going to move away from vectors with constant components and start talking about vectors that have function components. And these are called vector-valued functions. So a vector-valued function is a vector that has functions for each of its components. And just like before, we can write these with our triangular parentheses, or we can write them in the IJK format. The graph of a vector-valued function is a curve. And if it's a two-dimensional vector, it's going to be a curve in two-dimensional space. If it's a three-dimensional vector, it's going to create a curve in three-dimensional space. So some examples of what these are going to look like. We're not going to do anything with them yet, but just to see what they're going to look like. R of t equals 5t, 12 minus t squared, e to the 2t. So it's the same vector format that we've been using before. We're used to seeing just constant values in these three components, but now they're going to be functions of t. So our vector is not called just v anymore. The r is arbitrary. We could really use any letter for the name. If you think back to function notation from algebra, we were really allowed to name it anything that we want. And then in parentheses, we are saying what the independent variable is going to be. We could also write this in IJK format. So another example that is in terms of our standard unit vectors. R of t equals 3 cosine ti plus 5 sine tj minus 6tk. So just like before, our two notations are interchangeable. We could write the triangular parentheses here, or we could write IJK, and they really mean the same thing. This is considered vector notation. And what's going to really help us as we move forward with identifying and exploring some of the characteristics of these vector-valued functions is something also called parametric notation. So if we look just at this one right here, we could also get parametric notation. Remember, the first component describes what's happening in the x direction. Our second component describes what's happening in the y direction. And the third component describes what's happening in the z direction. So we could really break this down into individual equations and say, well, x of t, what's happening in the x direction is our values are changing by 3 cosine t. Y of t is 5 sine t. Z of t equals negative 6t. And this would be considered parametric notation. It's still describing the same vector-valued function, but it's just a different format that we could write it in. And there are some cases where this format is going to be more useful. So as in algebra, one of the first things we learn how to do with functions is just to evaluate them. And that brings about a whole discussion on, well, to evaluate them, we have to know what types of numbers we're allowed to plug in that will give us a real answer back. And that's called our domain. This is going to require us to remember all of our intricate little domain rules back from algebra class. So we'll review those really quickly and show how we can apply it to vector-valued functions. So first, let's talk quickly about some common domain issues that we see in algebra. Some characteristics of a function that would tell us, hey, I'm going to have to restrict my domain, or I'm not allowed to just willy-nilly plug in any number I want. And one of the things that we run across in algebra is when we have variables in the denominator. So we're working with some fractional expression and there's a variable in the denominator. And if we see this, we remember that we're not allowed to divide by 0, which means our denominator is never allowed to take on a value of 0. And we can use that fact to help us figure out the domain. We can say the denominator is not allowed to equal 0, and we solve for the variable, and it will lead to an expression or an equation or a list of values that we are not allowed to use for our variable. The second issue that we commonly run across in algebra are variables under an even root. So like square roots, 8th roots, 22nd roots. There are no issues with odd roots. We could take the cubed root of any number and we'll get a real answer. It's only the even roots that give us trouble. So anytime we have a variable under an even root as part of our function, we need to make sure that the radicand, and that's the name of the expression that is under the root, is always positive. We can't take the square root of a negative number. That will lead to complex numbers. And in calculus, we do not deal with complex numbers at all. So we want to make sure that the radicand is always greater than or equal to 0. And just like in the first case, if we were to solve this expression that we just set up, it would lead us to the values that we are allowed to use. Another common one that we're going to see are natural logs, or really any type of log. It could be log base 4, log base 12, the common log, which is log base 10. So the log comes up quite a bit. And just in case you don't remember, if you play around with your calculator a little bit and ask the calculator to find the log of some different values, what you will find is that we are not allowed to take the log of 0 or any negative number. So if we have variables inside a logarithm, we need to make sure that whatever values we plug in for the variable, it's going to result in our expression inside the log, which is called the anti-logarithm. It must be strictly greater than 0, because log of 0 is undefined, and then log of negative numbers are undefined. So these three are the most basic. They're the most common that we're going to come in contact with. There are some with trig functions, but we could always possibly refer back to denominator not equals 0 to help us with those trig functions if we need to. So let me show you a quick example of us trying to find the domain for a vector-valued function. So our vector-valued function is r of t equals square root of t plus 2, 1 over t minus 1, e to the 2t. The domain of a vector valued function is the intersection of the domains of each of our component functions. An intersection means we only want to know what they have in common. What values can be used in all three components. So the domain of a vector valued function is the intersection of the domains of each component function. So it's going to be more useful for us to look at these components individually. So our x of t is the square root of t plus 2. Our y of t is 1 over t minus 1. And our z of t is e to the 2t. And I broke these out into parametric equations because we're wanting to find the domain of each of them individually. So you can think of these as individual, their own little individual functions. So we're going to find three different domains, the domain for each of our component functions. So our first one has a square root in it. So remember, when we have a square root, our radicand must be greater than or equal to 0. So we're going to say t plus 2 must be greater than or equal to 0. And if we solve that for t, we get t must be greater than or equal to negative 2. So the domain for just x of t is negative 2 to infinity. Y of t has a variable in the denominator. And we said the one issue we could come across with that is that we plug in a value for t and then we get 0 in the bottom. And we need to make sure to avoid that situation. So we need to make sure t minus 1 is not equal to 0. And if we solve that, we get that t can't equal 1. So we're allowed to use any number we want except for 1. The interval notation for that would be negative infinity to 1, and we put a parenthesis on the 1 to indicate that we're not allowed to use it. And then also 1 to infinity. Again, 1 has a parenthesis. For our z of t, we've got an exponential function. And nowhere up here did we talk about an issue with exponential functions, because there isn't. We can plug anything we want to in for t, and we will get a real number answer back here. So technically, we can use all real numbers. So that's just a fancy symbol for all real numbers. All I've done is I've drawn an R and put an extra vertical line in it. So interval notation for all real numbers is negative infinity to positive infinity. Now we need to figure out what these three domains have in common. And the way that I like to do that, and I think it's the easiest way to do, is to graph them and see where they overlap. We only are interested in the sections of this number line where all three of our domains exist. So the first one says just negative 2 to infinity. So I'm going to go ahead and just mark negative 2 on my graph. For x of t, we are allowed to use negative 2, and we're allowed to use anything larger. So all the way to the right is positive infinity. For y of t, we've got to throw out the number 1. So I've got a big open circle on the 1. It's open because we can't use it. But we are allowed to use everything else. All the way down to negative infinity, all the way up to positive infinity. And then our z of t, the domain was all real numbers. So I'm going to shade the entire number line. Now for the domain of our vector valued function, I only want the sections of this graph that got shaded 3 times, which indicates they were part of the domains of each of our 3 component functions. So we could we could look at this in 3 different sections because I have 2 numbers marked. They break this up into 3 distinct sections. This first section does not have any blue shading, which means we cannot use that section. Our x of t is not defined there. This next section has all 3. It's got green, blue, and black. So we want to write interval notation that describes that middle section. And that goes, say the domain for R is -2, which was colored in, up to 1, which was open, so it gets a parenthesis. So this section works. And then if you look at the section to the right of 1, it's shaded all 3 colors, black, green, and blue. So we're also allowed to go from 1 to infinity. So sometimes if you have some pretty obscure or intricate domains for individual functions and it's hard to tell what they have in common, graphing them with some different colors might be helpful. Because then all we have to do is pull out the pieces that got colored all 3 times. So this tells us what numbers we are allowed to plug into our vector valued function, and we're guaranteed to get a real number answer back. So now we're going to talk about our first type of curve and our most basic curve that we can create, and that is a line. So no matter whether these lines are in 2 dimensions or 3 dimensions, remember that a line goes forever in both directions. So in order for us to describe this line in space, what we need is, in algebra, we needed a slope and a point. But we don't really have a description for slope in 3-dimensional space because we're working with 3 different axes. So the closest thing that we have to slope is a vector. A vector describes direction. It describes the direction that the points are moving in, or it describes how x, y, and z are changing. If you look at the slope formula from algebra class, it's y2 minus y1 divided by x2 minus x1. And we have seen these expressions before. These expressions are exactly how we take a vector that's given to us just as its initial and terminal point, and we put it into component form. The only difference is we don't stack them in a fraction and get a single value. We list them out individually, which is especially important since now we're going to have a third vector. It's kind of unclear on how we would incorporate the change of z into that fraction. So what we do instead is when we write a vector in component form, just as a reminder, if we know the initial and terminal point, we have x2 minus x1, y2 minus y1, z2 minus z1. So really, our component form of our vector describes the same things, and it also includes the z. So the 2 things we need to write the equation of a line in space are a direction vector, because that will describe how each of our 3 coordinates are changing. We also need a point. We need just 1 point on this line, and it can be anywhere. Because remember, a vector can be slid all around the plane or all around space, and it's still considered the same vector. Well, lines don't do that. Lines have to have a fixed location. So we can anchor this vector in a certain spot if I know a specific point that's also on that line. So v is called our direction vector. And let's say that V just has components A, B, C for right now. And then P is a point on the line. And we're going to say P is X sub 0, Y sub 0, Z sub 0. If I were to take any other random point on this line, and let's say we have no idea what the coordinates are, so we just call it X, Y, Z. The vector between P and this other random point that we'll call Q should always be parallel to vector V, because they're all pointing in the same direction. So Q is another, this time it's just a random point and we don't know the values, we don't know the coordinates, so we use variables. It's just another random point on the line. So vector PQ, and I'm actually going to do this, yeah, PQ. If I want to find component form for PQ, you remember you do your Q's minus your P's. We're going to have X minus X sub 0, Y minus Y sub 0, Z minus Z sub 0. This should be parallel to V, which is A, B, C. So remember what parallel means. It technically means that we could set those up as a ratio and they will all be equal. This is one format that we can write the equation of a line in. This is called symmetric equations for a line. So no matter what that ratio, the value of that ratio actually comes out to be, they will all be equal. Let's suppose that that ratio is equal to t, because we want to introduce a variable that allows us to move infinitely in both directions on this line. So let's say t is the value of that ratio. If we solve this equation for x, so we're going to multiply the a over and add the x sub 0 over, that leads us to x is equal to a times t plus x sub 0. And we're going to do this for each of them because all these values are equal, so they'll all equal t. And if we solve that for y, we get y equals b times t plus y sub 0. And then for z, we get z equals c times t plus z sub 0. This is another way that we could write the equation of a line in space, and these are called parametric equations. Just like earlier when you separate out your x, y, and z into individual equations, we call them parametric equations. And just a quick reminder, we took a vector valued function earlier and separated out into parametric equations. We're going to do that same thing in reverse. We have parametric equations, so we can take those individual xyz equations and actually write them as components of a vector valued function. So there is actually a third way that we could write a line in space. If we take each of these parametric equations, we could say r of t is AT plus X0, I, BT plus Y0, J, and CT plus Z0, K. And this would be a vector format for our line. Or vector valued function. So there are three different formats we could write the equation of a line in. When you work a problem, it's really up to you how you do it, unless the problem specifically states the format they want the final answer in. But all three of them are related, and all three of them just require the x sub 0, y sub 0, z sub 0. That's just a specific point that we are given on a line, and the direction vector, which gives us the a, the b, and the c. T is a variable. We actually call it a parameter. It makes sure that all of our values are moving in equal increments. And then x, y, z are like the output values, output variables, or dependent variables. So let's look at a couple examples where we figure out the equation for a line in space. And we're going to write these as parametric equations. And we're going to do two examples, so I'll give you some specific characteristics that we can use. The first one we're going to try, we have a line that passes through the point. -2, 1, 4. And it's got direction vector. V equals 1, 3, 2. So if you look back at the format for the parametric equations, we're really just setting up each of these individually are linear equations because we're dealing with an independent variable with a power of 1. The components of our direction vector just end up as coefficients. And then the coordinates of the point that the line passes through just end up as the constants. So there's really not a lot of work here to do. We're just going to say x is equal to, and then 1t minus 2. So I used my x component and my x coordinate. Y is equal to 3t plus 1. Z is equal to 2t plus 4. Now the 1 in front of the t in our x equation, that's just optional, but I wanted you to see in this first example where everything has gone. So we've got all of our components for v as coefficients, and we've got all of our coordinates of p as our constants. This is our final answer. This is what we were asked for. Oops. Parametric equations for that particular line. So that is like the easiest, most basic one we could do because they give us the exact information we need. Suppose we know 2 points that the line passes through. So let's say it passes through 0, 3, negative 1, and 4, 2, 5. So remember the two pieces of information that you need to write the parametric equations for a line in space. You need a point. Well, we've got that. We've got two of them actually. And we need a direction vector. That piece we were not explicitly given. So we need to figure out how to create a vector that's in the same direction as our line if all we're given is 2 points. Well, we could easily just label these guys as P and Q and create vector PQ. Since those 2 points are both on the line, if I connect them with a vector, that vector will point in the same direction as the line, so we can consider it a direction vector. So vector PQ is going to serve as our direction vector. Now, one thing I want to point out here, since they didn't tell us explicitly how to do this, you could create vector PQ or QP. Both of them would be perfectly fine. So I'm going to do PQ. That means I'm going to have 4 minus 0 is 4, 2 minus 3 is negative 1, 5 minus negative 1 is really 5 plus 1, which is 6. So this vector is describing how each of my coordinates change as I move from P to Q. And if we want to stay in a perfectly straight line, that's got to be the same amount of change we see as we jump from any point to another on the line. So now we've got our vector. And since we want parametric equations, we're going to have x equals, y equals, z equals. Remember, the components from our direction vector serve as coefficients because they describe change. And then when we go to do the constants in our line, you could use either one of those points and it would be correct. So if I use P, then I'm not going to add anything to my x because the coordinate's 0. For my y, I'm going to have plus 3. For my z, I'm going to have minus 1. So my coefficients were components of PQ, and then my constants I did from P. You could technically use Q as well, and you would get a completely different answer. You would get 4t plus 4. Y equals negative 1t plus 2. Z equals 6t plus 5. And this leads to a very important fact about lines in three-dimensional space, is that the equation for a line is not unique. When we're dealing with lines in the xy plane, there's only one equation for each line. But when we start working with lines in space, there are lots of different representations we can come up that will generate the same exact line. So the equation, and I'm saying equation just because we have 3 different formats, so I'm using that loosely. There's really not one single equation. There's really either parametric equations, vector valued function, or symmetric equation. But no matter which one we do, the equation for a line in space is not unique. And what that means is we could come up with several different answers that all generate the same line. So I'm going to circle this first set as my answer, just because I had complete free will on how I worked this problem, but there are many other correct answers.